All right, guys, Math 6620. The topic today is, or at least in this video, is log linear analysis, and it deals with categorical data, just as we've done in the previous two videos. If you think about what we kind of got accomplished in the two previous videos, we looked at the relationship between two categorical variables, and what I demonstrated. And again, let's think about two variables. And what I demonstrated in the previous video went accordingly. First of all, we carried out a chi-square test. And guys, in both of the illustrations that I did, I used a 2x2. You don't have to. You could use a 2x3 or 3x4, whatever. But the chi-square test sets up the null hypothesis that there's no relationship between the two categorical variables, and the alternative hypothesis says that there is a relationship. The second thing we do is we calculate the test statistic, and of course the p-value under the null hypothesis, and we use these to make a decision on the null. We have certain assumptions, guys. The most important assumption is independence, but remember we have this other assumption that says that each of the expected values, the model values, must exceed 5. Once we run our model to get a better indication of where the important components or cells lie, we can look at the absolute value of the standardized residuals and look at the ones that are bigger than plus or minus 1.96. Well, bigger than 1.96 since we're looking at the absolute value. I tend to think of this as a threshold of 2, so I tend to examine anything that's larger than 2. The fifth thing that you would want to do is calculate the odds ratio. Now this becomes a little tricky when you have like a 2x3, so a 2x2, I've already demonstrated that, but what if you had say a 2x3 and you wanted something, I don't know, maybe you had males and females, and you had it across UK fans, Ohio State fans, and Indiana fans. And the way I calculated odds ratios in the previous video, we couldn't make this happen. So what you would probably want to do here is you'd want to combine a couple of categories. It would depend on the focus. I'm a UK fan, so it's kind of like UK versus the world. So I would probably want to combine these two and make it a UK versus Ohio State and Indiana combined. Maybe not. Maybe again, just would really depend on the on what you want to look at. Guys, the final thing is report the results, and in APA style. And I showed you how to do that, I'm pretty sure, in the previous video. Okay, all right, guys, let's go on to the bigger, better stuff. Now, I want to bring this up. Log linear analysis. Typically, with log linear analysis, the way I think about it is we have more than two categories. More than two categorical variables. So we may end up with something like we wanted to look at. I think previously we looked at a problem about Professor A and B categorized the grades as a C or higher or D or lower. Well, what if you wanted to bring in gender into that analysis? So you'd have three categorical variables. Well, log linear analysis is the tool for you. We call it log linear. I'm going to focus on each part. We look at the log part because in order to transform categorical data analysis into a linear function, we look at a log transformation. And again, the linear function is kind of the end goal, that we can turn this analysis into something that looks like actually a linear model. Kind of think more of a general linear model, if you will. But I'll get into that throughout this video. So, guys, what if we had three variables? Again, professor, A or B, grade, C or higher, or D or lower. So we've categorized things here. If I was going to do something like this, I would probably keep this quantitative, but it doesn't serve to illustrate what I want to accomplish here, because I want things to be categorical. And we wanted to bring this in as gender, male or female. Well, guys, in a situation like this, if we just have two of these, we're going to use a chi-square. But when we have three categorical variables, we're going to use log linear analysis. Okay? Now, the general strategy that we implement in log linear analysis becomes clear if we think about our chi-square analysis as a general linear model. So we've got this chi-square analysis that we looked at in the previous video. I want you to think about this more broadly in terms of a general linear model, even more so in terms of regression. Now, what do I mean by that? Well, guys, in the spirit of general linear model, we know that our outcome can be expressed as our model plus the error. So, as we all should know now, in multiple regression, we could express our outcome as y sub I plus our model, I'm sorry guys, equals our model, which would be beta 0 plus beta 1 x 1I plus beta 2 x xi2. I can't, my writing is so small there. Okay. And we go all the way out to the number of predictors we have. Let's just call that b sub k, xi k. Well, this part is our model, but we're still going to have an error term or an error value, I should say, for each term. Now, guys, this is also similarly true for ANOVA. So again, ANOVA, regression, all this stuff meets out there someplace, and we call that the general linear model. Now, what I want you to do is let's start thinking about these categorical variables. And what I want to do is I want to go back to the political party versus, let's just call it beliefs. So we looked at a fictional data set that looked at beliefs about abortion, either pro-choice, pro-life, and political party, either Democrat or Republican. Now let's just revisit the data because I want to. We're going to get a lot more serious, I guess you would say. So let's set it up this way. So we have pro-life or pro-choice, and we have Democrat and Republican. And I want to code these as 0 being pro-life and 1 being pro-choice, and I want 0 to be Democrat and Republican to be 1. And guys, the count on these were 150, 400, 250, and 80. Now I want to put the expected count. The expected count for a Democrat who is pro-life is 250. The expected life for a Republican who is pro-life was 300. The expected value here was 150, and the expected value here was 180. So the observed values, and then we have our expected values in parentheses. Now, I want you to start thinking of these as dummy variables. Okay, and dummy variables are coded zeros and ones. And guys, we ran into dummy variables when we back in 5500 when we looked at multiple regression with categorical predictors. And if you just to remind you a little bit, a dummy variable, if we just have a dichotomous categorical predictor, then we just use zeros and ones as default. But if we get into a predictor variable that had more than 2 categories, then we had to create a dummy variable. And dummy variables, again, coded zeros and ones. You just choose a reference category and then just set up your zeros and ones accordingly. I would probably encourage you to maybe go back and look at one of those videos. Maybe, I don't know, maybe you won't need to. It's just depends. But anyway, what I'd like for you to do is I'd like for you to think about our problem being represented with dummy variables much like we would in regression. So I want to look at, first of all, the party, and then I want to look at the belief. And the way I always set these things up in this context is I always kind of look at the columns first, and I always look at the rows second. Okay? So let's look at the possibilities that we could have for party. Well, we could have a Democrat who was pro-life, or we could have a Democrat who was pro-choice. We could have a Republican who was pro-life, or we could have a Republican who was pro-choice. If we look at the dummy for party, letting Democrats be 0 and Republicans be 1, as I coded them before, then our dummy variables would be 0, 0, 1, and 1. We can also set up a dummy for belief, and pro-life, we said that was a 0. Pro-choice was a 1. I think, was that right? Yeah. And a 0 and a 1. Now we can also bring in, kind of in the spirit of kind of a two-way ANOVA, we could bring in an interaction term. And the interaction term is just the product of the two dummy variables. So we have 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and of course 1 times 1 is 1. So guys, we get kind of a presentation of our dummy variables as I've created here. Now, I think we all would have to be reminded of a two-way ANOVA in this context, where a two-way ANOVA, we have the impact of factor A, or we should say the effect of factor A, the effect of factor B, and of course the effect of factor AB. And that's essentially all we've done here with the interaction term. Now, we want to, let's start with a new sheet of paper here. All right, so again, guys, we go back to the spirit of the general linear model, where we have the outcome for I is equal to the model plus the error for the ith term. So we can think about this as the outcome for the ij component, the ith row in the j column, as b0 plus b1 times the belief plus b2 times the party plus b3 times the interaction plus the error term for that particular cell. Now, since we're using categorical variables and we have frequencies and not continuous measures, to make the model linear, we have to use the log values. Now, guys, we ran into this in Math 5500 when we studied logistic regression. I know it's been quite a while ago, but if you think about it, the dynamic between a linear regression and logistic regression is the linear assumption. And in a logistic regression model, the linear assumption is violated. So what we can do is we can, in the spirit of logistic regression, we could apply this logarithmic transformation to create, or I should say, to transform a nonlinear relationship into a linear relationship. So in regression, this allows us again to express a nonlinear relationship linearly. Now, and if you remember in logistic regression, I'm kind of getting on a tangent here, but we're going to really look into logistic regression after we get through categorical analysis. So I want you kind of to be thinking about this. There were two major terms that came out of logistic regression, and that was the legit term, and then we talked about the log likelihood. And, you know, all of these are kind of in the spirit of the maximum likelihood estimation. So what, if that stuff's a little fuzzy to you and you don't remember a lot about logistic regression, just hang on. We're gonna dive into that pretty deeply here in a couple of weeks. So, guys, our model for abortion and political party will end up being the natural log. And this is taking this up here. We're going to take the natural log to take the non-linear relationship and turn it into a linear relationship. So we take the natural log of the outcome for ij equals the model, which will be b0 times b1, which is times the belief, plus b2 times the party, plus b3 times, I'm just going to put a capital I for the interaction, plus the natural log of the error. Now we want our values to assume zeros and ones only. And since we can't use means like we could if we had a standard regression situation, we're going to use frequencies. So let's see how all this works out. First thing I want to do here is I want to examine the first entry in the table, and I want to examine 0, 0. Now, going back to the table, 0, 0, back when I gave you the table of the dummies for belief and party and the interaction, 0, 0 indicated what? Well, this indicated that the person was, let me get my sheet here. This indicated that the person was a a Democrat and was pro-life. Okay? So I can take the natural log of the observed value when the person was a Democrat, pro-life, equals B0 plus B1 times 0 plus B2 times 0 plus B3 times 0. Again, going back to, and let me grab this so I don't want any misunderstandings here. What I'm doing right now is I'm examining this row. And this row is comprised of a 0, 0, 0 for the dummy for party, the dummy for belief, and the dummy for the interaction. So I put those in as beta 1, or B1, B2, and B3. But guys, clearly what I get here is I get the natural log of the observed value for the Democrats and life, which was what, 150, equals beta 0. So guys, from this we can see that beta 0 is the natural log of 150, which is 5.0106, or at least that's what my calculator shows. Now if you think of this, this is just a log of the observed values when all categories are equal to 0. So one thing, a way to think about it, it's the log of the base categories. Okay, well, wouldn't you know it, my dog wants out. Hold on. All right, I'm back. I think what's going on, I think I figured it out. It's not that my dog wants to mess with my videos. I think my dog is sleeping, and when I start talking, it wakes her up, and she thinks, well, let's just go outside. All right, gang, what I want to do next is I want to look at the next entry, which is 100. So that's going to represent when we have let's see, 10 is going to be when we have a Republican who is pro-life. So we want to take the natural log of the observed value for a Republican who is pro-life. And this is going to be B0 plus 1 times B1 plus 0 times B2 plus 0 times B3. Okay, I have no idea what happened, but my screen just went kind of wacky there. Huh, well that's really strange. Well, guys, I don't know what happened there. I'm going to quit this and bring it back up and see if that... yeah. Okay, I have no idea why that thing just all of a sudden collapsed on me. Guys, what we have here is we'll have the natural log of the observed value for a Republican who is pro-life as B0 plus B1. So guys, at the end of the day, we can see that B1 is equal to the natural log of the observed value for a Republican who is pro-life minus B0. So guys, I get the natural log of 250? No, wait a minute, that's not right. 10 the party being 1 in the belief, that's going to be 400. And B0 is 5.0106. And let me grab my calculator here. And guys, I get 0.9809. All right, as you would expect, the next thing I would like to look at. Now, I'll tell you what. Let's go back and think about what this is. This 101. If you think about what's going on right here, let's put into words. What does this B1 actually represent? Well, this is really just the natural log of the observed difference of a Republican who is pro-life minus, if we go back to B0, we remember that that was just the natural log of a Democrat, the observed for the Democrat being pro-life. So if you think about that, you can think of this as, again, being B1, and at the end of the day, B1 is just within those who were pro-life. This is just the difference between the Republicans and Democrats. So we can think of that kind of as the for the difference in the party. Let's now examine the other. And guys, let's examine 0, 1, 0. And what this is 0, 1 would be a Democrat who is pro-choice. So we're going to need the natural log of the observed for a Democrat who is pro-choice. Guys, I have no earthly idea why this is happening, but this is really annoying me. I'm going to shut this down one more time. It is it's collapsing on me, which is extremely strange. So this is going to be beta 0 plus 0 times beta 1 plus 1 times beta 2 plus 0 times beta 3. So guys, at the end of the day, we'll get that the natural log of the observed value when a Democrat is pro-choice is beta 0 plus beta 2. So therefore, beta 2 is just the natural log of the observed value when we have a Democrat who is pro-choice minus beta 0. And this value, a Democrat who is pro-choice, is 250. Okay, so let me put that in the calculator. And we get 0.5109. All right, now I'm going to leave that for you to figure out what that is, because that's going to be certainly something you're going to encounter on your homework assignment. But from the previous example, looking at 100, that should be pretty obvious. Well, gang, you probably know where we're looking at now. We're going to be looking at 1-1. So 1-1-1, and then the interaction term gives us a 1-1-1-1. So this is telling us, this part right here tells us with the coding of 1-1 that we are looking at a Republican who is pro-choice. Those are probably pretty rare. All right, so the natural log of the observed for a Republican who is pro-choice, and this is going to be B0 plus B1 times 1 plus B2 times 1 plus B3 times 1. Now, let me just go. I was going to skip a step, but don't want to do that. So again, we already have B0, B1, and B2 calculated. So this tells us clearly that B3 is going to be the natural log of the observed value for a Republican who is pro-choice, minus B0, minus B1, minus B2. Guys, I'm going to leave this for you guys to work on. Clearly right here, we're going to put in 80. And when I work all this out, I get negative 2.1204. And guys, as always, I really do encourage you. Nat, keep me honest out there, man. Make sure that I entered everything completely. Well, guys, that leads us kind of to the drum roll, please. We now know that the natural log of the observed values for our cell of the ith row in the J column can be found by beta 0 or B0, which is 5.01, plus 0.98 times, guys, I've lost my 0.98 was the belief, plus 0.51 times the party, minus 2.12 times the interaction, plus the natural log of the error term. So guys, we would refer to this as our full model. Now, just to show you that there's nothing really crazy going on here, what I've done here is I've created an Excel spreadsheet, and what I've done here, you can see it's a really large spreadsheet. It's because we have 880 participants here, so it goes down to 881 considering the first line is the headings. And what I've done here is I've gone through and looked at all the situations. So of those who were party 0, which is Democrat, and belief 0, which is pro-life, I have the interaction as 0. The observed count was 150, and the expected count was 250. Now what I've done here is I've done this for all options, okay? And then I came in and created a natural log of the observed, and that was just clearly taken, or simply taking the natural log of 150. And over here, the natural log of the expected was 250. Now guys, I've uploaded this video, I will ultimately upload this video to Blackboard, but I've uploaded this data set, this Excel spreadsheet saved in .csv format to Blackboard, okay? So I'm just going to go ahead and save this. And guys, I called it, what? I called it belief. I think I've got it on my desktop. I got it beliefs. Okay, so I'm gonna go ahead and get R going. And it's been a while. Remember how we do this? And I'm going to bring open my data. And I got to attach my data. And I like to look at the names. So guys, that's the way we need to type things in. Now, remember the model we had, and what I can do, I think this is always kind of good. Let's go ahead and just look at a table just for party and belief. And you can see that the contingency, or the distribution of frequencies is exactly for zeros and ones, as we need it to be. But what I want to do now is I want to, guys, remember, we're talking about the natural log of the observed. Every single calculation that we made used the natural log of the observed count. So what I'd like to be able to do here is I'd like to just create a model, linear model of the natural log of the observed as a function of party plus belief plus the interaction. Now, if I look at my model, you'll see that some things pop up that I knew I had that messed up. I sat there and said it, and I couldn't believe I was saying it. Notice the party is 0.90808, and when I went back to the interpretation of the 1 0, that was obvious. And I don't know why, but I sat right there and said it, and I knew it was wrong. So what I did, let me go back and show you. What I did is I went in, and the 0.98 should actually go with party, and the 0.51 should actually go with belief. And such a bozo. I knew it was wrong when I said it. So, but anyway, you see the B0 is 5.01, and the coefficients match up what we created by hand. Now, something kind of interesting, if you do a summary of your model, let me get back into R. If you do a summary of your model, where you get your standard errors and so on and so forth, this is, you know what, I would like for that not to be in scientific notation. Okay, let's try this. Options, psi pin equal 999. All right, let's do it. I think that gets it out of scientific notation. Whoa, it does. Okay, all right, that's cool. So our estimates now are not in scientific notation. They're kind of in annoyingly long display. But something I want to show you is look at the standard errors. The standard errors for each of these are essentially 0. And when we get this situation in a general linear model perspective, we call this a saturated model. And it's interesting here because this is, you're not going to see this in ANOVA, and you're not going to see this in regression, where the standard errors are 0, but because we've accounted for all the possible various combinations, in essence, there leaves no room for the imagination. So there's actually no error because the cells completely explain the observed value. So guys, again, this is known when your standard errors are all 0. It's known as a saturated model. They show up in this perspective. They don't show up much in ANOVA or regression. So guys, anyway, you've seen a demonstration here. So at least temporarily, I hope you see that the chi-square statistic that we saw in the previous video can be conceptualized as a linear model with an interaction term. Now, where do we go from here? You know, when we talked about the chi-square model before, there was no mention of this interaction term, right? It was just we look at the cells as they stand without any examination of an interaction. In other words, we're more interested in just what is the unique effect of each of the particular cells. So now I want you to consider now, what would the model look like if we eliminate the interaction term? So let's go back to this, if I can get this working okay. And it's collapsed on me. Guys, I've got to get that fixed because that's going to drive me insane before the end of the term. So what do you think we'll do? Well, the solution to eliminate the interaction, again, because there was no mention, I kind of just slammed you with this interaction thought, kind of randomly. There was no discussion of the interaction component when we talked about the chi-square in the previous couple of videos. So again, I want to look at how chi-square can be conceptualized as a linear model, just looking at the unique effects. So guys, we can think about the natural log of the observed components as, again, looking at just the beta 0 plus beta 1 times the party plus beta 2 times the belief plus the natural log of the error. So let's get rid of the interaction term. So this leads us to get the natural log of our model. For I sub j being b0 plus b1 party plus b2 times belief. Now, how did I magically go from here to here? Well, again, if you solve for this right here and bring the natural log of E sub I across here, the observed minus the expected is just our model. So, guys, this is going to be made easier because our model is just the expected value. So we switch our focus from the observed value to the expected value, being found by b0 plus b1 times party plus b2 times the belief. So guys, the first thing I'd want to do here is I want to examine 0, 0. And again, 0, 0 is when we have a Democrat who is pro-life. So I'm going to take the natural log of the expected value of a Democrat who is pro-life equals beta 0 plus beta 1 times 1 plus beta 2 times 0, 0. Guys, listen to what I intend to say, not what I say. So guys, at the end of the day, we can say that beta 0 is the natural log of the expected value for a Democrat who is pro-life, and the expected value for that was 250. So the natural log of 250 is 5.5215, telling us B0, the base is 5.5215. What I'd like to do now is examine (1, 0). And I'll tell you what, let's see. Let me start a new sheet of paper. And it's getting annoying. I'll tell you what, I uploaded to this Yosemite operating system, and I've had more stability issues than ever before, so I'm not sure that was a good move. Maybe it was a great move. Maybe I just don't know what I'm doing. So I want to examine, I didn't say that. I want to examine 1, 0. So guys, 1, 0, I'm going to take the natural log of the expected, and 1, 0 is a Republican being pro-life, equals B0 plus B1 times 1 plus B2 times 0. So at the end of the day, the natural log of the expected value for a Republican being pro-life is equal to B0 plus B1. So B1 is going to be equal to the natural log of the expected value of a Republican being pro-life minus B0. So we have the natural log of the expected of Republican being pro-life is what, 300 minus 5.5215, and guys, I get 0.1823. Guys, I want to examine 0, 1. And when I get this, I'm just going to go ahead and just kind of cut to the chase here. When I get to this, I get that B2 is equal to the natural log. So 0, 1 would be a Democrat being pro-choice. Minus, so I've got 0 and 4, so this is going to be minus B0, right? Yeah. And so my expected value is going to be in here 150. So this is a natural log of 150 minus 5.5215. And when I put that in my calculator, I get negative 0.5109. So guys, at the end of the day, I would end up with a final chi-square model. In linear form as the natural log of the observed. Now guys, I know I made the calculations using the expected, but I'm going to come in with the natural log of the error term here, so that's going to move me back into examining the observed value. So guys, beta 0 is 5.5215. And it was plus 0.1823 times party plus 4.823. No, wait a minute, that's not right. I'm losing my mind here. This is actually minus 0.5109 times belief plus the natural log of the error term. Now, That doesn't seem like what I get. 0, 1, 1, 0. Yeah, all right, let's go for it. So guys, if we go into back into R, and again, I want to go names, data. So what I want to do now is I want to create model 2. But this time I want to do it as a linear model of my expected, natural log of expected, as a function of party plus belief without the interaction. Okay, so you'll see that we do get the negative 0.5109 for belief as we would expect that we would get. Well, to stop or go on, what should I do? I'll tell you what, I think I'm going to stop this video here, and we're getting ready to have some fun. This is getting ready to get pretty cool, but again, just kind of setting the foundation for some pretty cool stuff. So what I want to do next time is I want to consider a situation like this where we look at beliefs about abortion, either pro-choice or pro-life, across political party, Democrat or Republican. And let me tell you, don't go out and run around and say, yeah, Darborough had a data set that showed that there's a clear relationship between that. I actually made this up. I worked, tweaked it or torqued it or whatever you want to call it, to where it would create a certain situation, but that it has. But what I want to do from here is, what if we added gender? What if we not only knew the party of the person and the belief, but what if we added in a third categorical variable, gender? How would we do that? And that's where really the log linear analysis really starts to